Hey, what's up? So I'm continuing the 6502 assembly stuff, which I've been learning, but we're making a lot of progress. So this is not me teaching the world. This is me sharing as I learn. And so I'll go over what I've done so far, what my medium-term goal is here, and if you're picking up where we left off, yeah, we'll get to it. The medium-term goal... Okay, so let me give some context. In the past, maybe 6 months ago or so, I tried to learn basically Nintendo Entertainment System programming, which is 6502. And in hindsight, I think that it was a little overwhelming to both be learning the assembly stuff while also trying to learn some of the details about the Nintendo Entertainment System. Like, in particular, the NES has... It basically has a graphics chip, the PPU. It's called the PPU. And there's some weird things that are done because they're dealing with a lot of constraints at the time. And, yeah, it's a little bit confusing. So this time around, I mean... I'm not just interested in NES programming. The 6502 in and of itself is of interest, but I'm just focused on the assembly side of stuff. So I've chosen I want to write a program that does something specific I'll talk about in a second. And, yeah, so what am I doing? Well, basically I want to write a program that... It gives you permutations. So, in other words, it gives you all the possible orderings of a certain number of items. So, if the program receives the number 3, as an example, it will output all the possible orderings of 3 elements, all the possible permutations. So, for example, it will output 1, 2, 3, 1, 3, 2. Right, all the possible permutations. 1, 2, 3, 1, 3, 2. There's 6 of them, and there's 2 of them where 1 is unchanged. And okay, then let's see. We can have 3, 2, 1. This is where 2 is unchanged, and then we can have 2, 1, 3, that's where, so 3 has been unchanged. And there are 2 more that we're missing. I know that there's 6 of them. Let's see, so I see that we only have one with a 2, starting with a 2, so we can have 2, 3, 1, and then we're only starting with a 3 on this one, so we also have 3, 1, 2. So these are the 6 permutations. And so the idea is that as input, the program would receive the number 3, and as output, it would spit out this. I don't really care about the order that it spits it out. So that's a bit of a challenge. Obviously, the amount of output scales up quite quickly, like because it's this has 6 output. It's because it's 3 factorial. So for the first choice, you have 3 possibilities, and then you have, for the next choice, you have 2 possibilities, and then for the last one, you have 1. So if the input is 6, we're going to have 6 factorial. I don't even know what that is. I mean, I think 4 factorial is 24, I think, I'm guessing. 5 factorial is probably 120, and 6 factorial is like 720, something like that. So it spirals upward quite quickly. Anyway, that's a bit of a challenge, actually, and it's an algorithm I'm interested in. Well, I guess it's a challenge I'm interested in, and there's probably multiple algorithms. There's one specifically that I want to do. Now, yeah, so I do kind of want to, let me see here. Let me see if I can bring up the day 1 and day 2 stuff here. Hold on. Let's go here. The Ramon Magsaysay Awards presentation. 1 second. just kind of looking for my own channel here. Live streams. I basically put the product of what I created in the descriptions here. So let's see. This is the first one. And I put it as a comment and also as a description here. So let's see here. So this was day 1. So let's look at what I had after day 1. So we don't need this to be over there. Okay. So I'm treating this as the input to the program. And I'll explain what all of the instructions do. So LD, it loads into a register. So this loads the number 4 into this register X. So the program has, in 6502 you have 3 registers, X, Y, and A. A is called the accumulator, but we can just call it A, it doesn't matter. What this does is it basically stores X in this memory location, which is memory location 1 here. And this will basically send the number 0 to the Y register. It's load Y with whatever this is. And this is the number 0. The $sign says it's hexadecimal, and the number sign says treat this as a literal number. Okay, so we're basically starting the program, taking the input, number 4, storing it at this place of memory. Okay. So let's write store input of program into memory location 01. That's basically what that does. It's the X register. Okay. And so it's load number 4. I'll put it in quotes, I guess. Into X. This is load 0 into Y. I don't think I needed to use hexadecimal at all, but whatever. Okay, so loop. We've got a loop here. Okay. This is not a keyword or something. You could call this whatever you wanted. Here I called it loop 2. And I believe what we're doing here is we've got well, the second loop is basically going to be output. You know, I wrote it that way. And so, hello, is that Karun? Is that your name again? It's been a little long time no see. How are you doing? Okay, so we'll walk through these instructions. So this T is like transfer. Kuma Bear, the cat, he's doing fine, I think. Yeah. Kuma Bear. So T is like transfer, so this transfers X to A. So write that. Transfer X to A. Here is, now we're using the stack. I ended up changing this later. Korun. Uni? Uni. All the cats are good, yeah. How are you doing? So this is going to, let's see. Yeah, this pushes, I believe this pushes A, whatever's in A, onto the stack. So a stack is like what it sounds like. Imagine you're stacking plates. So you put the first thing on the stack, and then the second thing on the stack, and then the third thing on the stack. When you pull from the stack, it pulls from the top. Okay? So anyway, we're taking whatever's in A and pushing onto the stack. So that's our first thing on the stack. And it went from X to A to the stack. So X was our input, which is the number 4 here. And so we push that onto the stack, basically. Okay, take care. Push A onto stack. This increments y. So I'm using, I believe I'm using, let's see here. Because we need to increment something for the loop. But this is a decrementing x. So, decrementing x. Let's see here. So y started at 0, now it's at 1. And x started at 4, and now it's at 3. Then in this line, what we do is we compare x with the number 0. So because x is 3, this compare basically returns false. But what actually happens is there's a z flag, like the 0 flag, and I think of this as returning false, and it sets the 0 flag to 0. If it returned true, it would set the flag to 1. I mean, that's very typical in programming. 0 is used for false. 1 is used as true. So this compares x to 0. Yeah. And sets z flag accordingly. Okay. Now this BNE is it's branching. So branch on not equals. So in the first iteration, x is 3. We're comparing to 0. It returns false, basically. And so, in other words, they're not equal. And so it will get to here, branch on not equals. So it will branch because they weren't equal. And it goes here. Now I could have done this like go to loop 2 or go somewhere else. These are labels. So it's like a go to. Okay, so on the first iteration, x got decremented to 3, and then it loops back around. It takes x, pushes it, well, it transfers it to A, and then pushes that onto the stack. So at first we had 4 on the stack, now we have 3 on the stack. Increment y, so now y, it started at 1, but then it was incremented to, or sorry, it started at 0, was incremented to 1, now it's at 2. Then decrementing x, now, so x started at 4, went to 3, and now it's x is at 2. Now we compare again, it's not equal, so we're going to loop around again. It's going to now, so x is now 2, it's going to push that to the stack. It's going to increment y. I don't need to be incrementing y at all. It's not used, is it? So that's a mistake. I'm going to leave it in because I'm just going over the code that I made on day 1. Yeah, we don't need y here at all. So I think we're now to x is 1, and then it'll go around the loop again until x is 0. And when x is 0, it compares here. I think of it as returning true, but what it actually does is it sets the z flag, the 0 flag, to 1. And then when it comes here, what that does is it doesn't, this line basically does nothing. And so it doesn't branch, it doesn't go here, and it just goes to the next line. Now, this instruction is load the number 0 into y. So I'm just I'm setting up some variables before we go into the second loop, and the second loop is where we're going to output. Notice that what this loop did is it pushed things onto the stack. So we have 4, 3, 2, 1 on the stack. Okay. And so we load 0 into y, we load the number 1 into x. Okay. So PLA, what's that going to do? That is going to... Oh, my tabs are what? Tab right now is 1 space? Who the heck came up with that idea? Or whatever. Wait, what? Indent using tabs, please. What is... I don't know. I don't know what the heck is going on. Anyway. So this is going to take whatever's in... So this is not push... It's not PHA, it's PLA, so it's going to pull from the stack. So put this out here. Pull from stack. Okay, so at first it's going to... So the stack put 4, 3, 2, 1. And now when we pull it, it goes from the top. Pulls whatever's at the top of the stack. So it's going to pull the number 1. So 1 at first. Then we have STA. So STA is basically store A, the accumulator, to this memory location. So this is a memory location with an offset. So to memory location, and this is hexadecimal with the Y offset. Now Y we sort of initialized here as 0, or we assigned it 0. So in the beginning there's no offset, so it writes here. Now in the thing that I was using, this corresponds to the first pixel on the screen. That's going to be implementation specific depending on what you're doing, obviously, so in this particular case that's what it did. So yeah, the number 1 is being put there. Cool. Then we decrement x. Decrement x. So x started at 1. Now it goes to 0? What? I'm a little confused by that. Decrement x. Huh. Not sure if this is going to work the way it's supposed to, actually. Maybe... Anyway, increment y. Compare x to the number 0. Branch on not equals loop 2. I'm a little confused. We have set x to 1. So let's actually put this into the thing that runs code, which we have right here. Assemble run. Okay, it's working. So something is wrong in my brain. There's notes here where it tells you what number corresponds to what color. You can see it down there. So actually, white is the number 1, red is the number 2, cyan is the number 3, magenta is the number 4. Sorry, 0, 1, 2, 3. No, it's 1, 2, 3, 4. Yeah, 1, 2, 3, 4. And that was sort of the goal of what this code was supposed to do here. So let's see. Hold on. Something in my brain is not working correctly. We've loaded number 1 into X. We're pulling from the stack. We're storing that number with offset Y. We decrement X, increment Y, compare X with, hold on. Yeah, compare X to 0. If we decremented X, if X started, oh, okay, I understand, my mistake. So this does not load the number 1 into X. It would if there's a number sign here. This loads whatever is in memory location 1 into X. Okay. And what is in memory location 1? Well, we stored the input of the program. We stored the number 4. So it starts, so this sets the number 4 into X. So, okay. So X here gets decremented to 3. We compare. And so right here. First it gets set to 3. Then on the second iteration here, it's going to pull from the stack the number 2. It writes that to the next pixel. Now, y started as 0, but then it went to 1. So on the second iteration, there's this y offset, which is 1. So that's going to increment this memory, basically. This memory location, and it's going to... it is going to, yeah, store whatever's in the A register into the, basically the second pixel. Then we decrement again to increment. It compares the number 2 here to 0, and it's going to loop around. Then we get the third value on the stack. It'll write to the next y value, y got incremented, or the next location of memory. Decrements to 1, increments to 3, goes back around, gets 4, writes 4, decrements to 0, and then increments, and then now it gets compared and it stops the loop. I don't know why this says transcript. And that's it. So this is a pretty simple program that just, given the input 4, prints this out. So let's see if I give it the input 8. You can see that it does this output, which basically corresponds to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that was day 1, just learning to do this. And I'm going to, let's see. I'm going to comment this. So I don't think I needed this y here, but I'm just going to leave it in as an Easter egg of a bug. I'm going to comment this on the YouTube page there. And note that I don't think we needed increment y in the first loop. But I'm going to leave it there so that people don't get confused. Alright, so that's added to the first video. So then we have the second video here, which was yesterday. Streamed live 23 hours ago. And let's just walk through what this code does now. It's similar. And in fact, I mean, it's up here. It is all of this. Alright, so one of the things I figured out yesterday is that you can sort of, these are like macros. You can say, you can basically attach a label to a location of memory. You might be able to just do this with numbers and stuff too, I think. But so instead of writing down here in the previous day, I was using this location in memory to store the input of the program. But this kind of appears as a magic number that can be confusing. You see I got confused on it in real time here as well. So instead of that, we have this sort of label. I call this a macro. That's sort of probably like C and C++ language, and various programming languages. I'm not sure what they call it for assembly, but you'll hear me call it a macro or a define, something like that. Yeah, so we use that instead, and then we have memory here. Now, where I left off, I was going to make a function that transposes two elements. So we had it before. I was writing out all the permutations that can happen with 3 elements. Those are all the permutations. And so, for example, from here to here, you can get from one to the other by swapping the second and third elements. So I wanted a function that just swaps. Or, I mean, you'll hear me say transpose as well. Transposition is sort of the mathematical term. But we're just going to swap two elements. So I want a function that does that, and so it needs input. We need two arguments to the function, essentially. And so I was thinking I'd do that on the stack. Just take the input, or sorry, take the two arguments that I want to the function, and I was going to push that onto the stack. Now that might work. I'm not exactly sure. Because I'm kind of new to this stuff, and also there's some weird things that happen with the stack, I think, when you call functions. I'm really not sure. I say call functions. I'm using some of the lingo that's probably meant for higher level languages, but hopefully people get what I'm saying. Because these aren't really functions, they're just labels, I guess. But whatever. So that's what I was going to do with the stack, but I think... Not sure if that's the best way to do it. I was watching some videos earlier today, and I think instead I'll just specify some place in memory that corresponds to the arguments to the function. So like I might do define swap arg1 as memory location 3, define swap arg2 as memory location 4, and so on. I'm going to go with that route because that's kind of what was suggested. There's many ways to do things, I know, so we'll have to figure out as we go what the best way is. But anyway, and different programmers are going to have different styles. But I'm going to go with that. In any case, let's explain what this does. So we have this write out function. We've got this write to memory. Function, we have init. So I ended up organizing the code a bit like this. So we init. So this JSR is jump to subroutine. That's basically like calling a function. I'm still treating this like the input to the function. And notice that we have these sort of labels or macros. We'll see that later. But okay, so we start with the input of the function. And then we jump to the subroutine init. Okay, so let's see what init does. It sets the Y value to 0, the Y register. And then it stores whatever was in X into this input memory location. In my example, X, we're starting as 4. So it stores that as input. This is meant to represent the input of the program. It's not literally input to the program, but kind of just treating it that way for now. We're pretending. And then what's this? LDX. So this... What are we doing here? Oh, okay, so... For whatever reason, I'm setting X to 1. We'll find out why later. So Y is getting set to 0, X is getting set to 1, and we've stored the input away. And then RTS is to, it's basically a return. I think it's return subroutine maybe, but anyway, it's basically a return, so it's going to go to the next line. It's just like calling a function and then returning. So then we go to the write to memory function, which is here. This is going to amazingly write to memory. So the STX, the memory, let's see here. Okay, yeah. So I just chose an arbitrary spot in memory. And with an offset Y. So Y started as 0, so it begins with 0. So in the previous example of the previous day, in the code I wrote for the previous day, I had been using the stack to store information. And then working on it more yesterday, I thought the stack is going to be very useful for all kinds of things. And I didn't really want to use the stack to... Well, I thought I want to keep the stack if I can for other stuff. So instead of writing to the stack, I just write in somewhere in memory. And that's what I did. That's what I'm doing here. Then we're incrementing y, so it gets set to 1. CPX input is comparing x with input. Okay. So at first, that is going to be x at first. What did we start with? Was it 0? It's 1. We started with 1. 1 and input, which is 4. So when you compare 1 and 4, they're not equal. Now what this does is it's set, so when if they're equal, it sets the Z flag to 1. But I think it also sets the carry flag. And I don't know if I'm doing something weird, but I realized that if you want to have something here before you branch, you can use, instead of like branch on not equals or whatever, BNE, we can do this other BCC, which is branch on carry or something like that. Yeah. For whatever reason, I wanted to increment before we branch. So at first x was 1. Now x is 2. We're going to go through a loop here a little bit more. Y was 0 but got set to 1. So now there's this y is this offset here. So store x to memory plus, I'll just say memory plus y. Memory. This is like a pointer right now in a sense, and then it's an address in RAM, and y is the offset. So x got set to 2. So on the first iteration of the loop, it stored the number 1. Now it's storing the number 2 with an offset. So the first pixel was 1, second pixel is 2. Except it's actually, it hasn't written it to the pixels. It's just in memory. It's right here, starting right here. Cool. And let's see. So now it's going to compare the number 2 with the number 4. It increments x to 3. Loops back around. It's going to write the number 3. Increments this to, I think I skipped incrementing this before. And then now it compares 3 with 4, and we're going to loop again. It sets this to 4, blah, blah, blah. And now it's going to write the number 4. So it wrote 1, 2, 3, 4. This doesn't really matter because we're going to exit in a second. Now it compares 4 and 4. And it is going to set the carry flag, which is going to cause this to stop looping. So this is actually, I believe this is branch on carry complement. So it branches when carry is 0. Now the carry flag is getting set to 1, and it's not going to branch. Then we RTS, we return. So we've written the first permutation to memory, essentially. But we still haven't sort of printed it out, so to speak. But that was this. Now we're just setting the y value to 1. This clears carry. Clears the carry bit because that got set here. I'm not sure if the carry, if the flag, you know, when you JSR, if it gets reset or something. I have no idea. But just to be safe, I cleared it. Clears carry. Now we're jumping to write out, and that will be the end of the program. Yeah, so... But notice that we set y to the number 1. Okay, try to remember that. So what this is going to do is loads whatever's here into x. So this 0, 1 was... Okay, so what I'm actually going for is memory. And note that y is 1 here. We did that here. So y is 1. I don't really remember why I did it this way, instead of like having y 0 and then LDX with the memory location. But whatever, this is going to go to the first spot in this memory address. And it is going to load it into x. In other words, the first will be the number 1. Because we wrote 1, 2, 3, 4 into memory. So at first it's going to be the number 1, loads into the x register. Now we transfer x to A, so the number 1 will be transferred to A. STA, what is this? So this stores whatever's in the A register to this location. This is 1 before 0, 200. 0, 200 is where we actually write pixels to the screen. And so because y starts as 1, in the first iteration of this loop, it will write to the first pixel. Y is not starting as 0, it's starting as 1. Now we compare whatever's in y to input. Input was 4, so it's going to compare 1 and 4. That basically returns false, but what it's going to do, it's going to set the z flag to 0. Now we increment y. So y was 1, now it's 2. It's going to loop around. We'll talk about this again at the end, but y is now 2, and we're looping back around. So now this offset is incremented 1 forwards. So it's now going to load the number 2 into here, send it to the A register. Then it's going to store the A register. Again, the y is being offset here 1 forward, so it's the next pixel. And yeah, so this is just going to take that 1, 2, 3, 4 that was in memory, and it's going to change it to this other location in memory that corresponds to the pixels. Seems a bit roundabout. Why not just write things straight to here, which you could do. But the thing is that I want to create all the possible permutations, so I want, before writing things out, I want to have some space to work with things a bit. Baba Liberty, thank you. Thank you very much. Yeah, and so y gets incremented. There's another loop. Y gets incremented. So when y is 4, it's going to come back around. That's the 4th pixel, basically. And it's going to output that. And now it's going to compare the number 4 to 4. And now this CPY, basically it returns true, which is going to set the carry flag so that when it comes here, let me think. Does it set the carry flag to 1? I forget if it sets the carry flag to 1 or 0, to be honest. But the important thing is it changes from what it was doing before, and the loop is going to end here. So that is what it does. That's what I was doing yesterday. I'm going to get rid of some of these little added things that I wrote here. So we have this commented. Cool. So now what I want to do next is implement this swap function. And so that's going to take two things and switch the values. Yesterday, I got confused trying to learn about the indirect addressing, which is here. Now, I believe there's a typo here. I also didn't see... So the first address gives the least significant byte of the address, and the following byte gives the most significant byte. So instead of, and also this is not supposed to be 0, 0. I think this is supposed to be F1. So let's explain what this does. So this loads the number 1 into A. So loads the number 1 into the A register, also called the accumulator. This stores A into the memory location F0. Now this one is going to load the number, so it's a hexadecimal number, into the A register, and then it stores A into memory location F1. Now, I believe this is supposed to be F1. And so you might think, so CC is here. Let me think. The first address gives the least significant byte. My brain is getting confused, but it's the opposite of what you would think. You would think F1 has CC, so I think it's supposed to be F0 F1. You would think that it goes basically in F0 we put 1, so you'd think it would be 0 1, and then this F1 is CC, but it does it the opposite order. Why does it do that? It was probably easier and cheaper to implement that in hardware for the chip, I'm guessing. Now I think that that's how it works right now. I haven't really tested this at all, but so this parentheses here is basically indirect addressing, and so it's like using a pointer. In other words, it is going to look at the space in memory, and then it is going to use what's there as an address in memory. Anyway, so I think we'll be using that at some point. We'll get to it when we need to, and we'll test it and all that jazz. What I want to do is I want to take this and copy it into here so I can actually run it. So let's see, assemble run. Okay, so it's outputting 1, 2, 3, 4. So now I want to implement this swap function, basically. Let's see if we can just kind of make this bigger, like that. It's good. And then, okay. So what I'm going to do, instead of using the stack for the arguments of the function, I'm going to make some defines. So I'm going to say swap arg1, and we'll just set that. So, okay, now we have a problem. I need to move this. So actually probably, maybe using the stack for this was better. You know what I'm going to do? Instead of using memory 2, I'm going to use the end of the memory and work down, so that I don't have to change this value. So I'm going to say, I believe the end of the memory is, well, I say the end of the memory. The memory is broken into different regions, so let's see. They talk about that somewhere. And memory RAM is pretty interchangeable. Let's see, do they talk about it somewhere? Well, there is, okay, so here we go. It's a 16-bit address bus. Okay, so this is all you have access to in memory. It's going to be this many bytes. So this FF in hexadecimal is 65,535 because there's an extra byte for the number 0. But with what we're doing here, the address 0200 in hexadecimal is where we store the pixels of the screen in this implementation. So anyway, I want to use the 0 page, which is the first. First of all, it's a little faster to use the 0 page. It's a little convenient to write. So that's 1 byte of information. Hexadecimal, when you have this like 2 digits in hexadecimal, that's 1 byte. It's 256 possible values. So I'm going to use that. And so I'm going to work from the end and work down. So FF should be the last possible value there. And so A, B, C, D, E, F. So E, right? A, B, C, D, E, F. This will be the second last, and we'll have that as arg2. Okay, so before calling the swap function, we need to set these. So let's see. I'm going to put this down here just and comment it. I'm just going to comment it so that we have it as information. So we're going to have the swap label thing. Yeah, so we just need to take these 2 things in memory and swap the values. That's the idea here. That's all this function needs to do. Now, I'm pretty new to this stuff, so I don't know, like, using the X register and Y register and all that here might be a bad idea. But I'm going to do this, and then if I run into problems, we'll fix it later. So I'm going to load into X whatever's here. So I believe I can just do like this. And let's load into Y, the second argument. And now the way that you swap stuff is that you have like a temp variable. So I'm going to transfer X to A. Transfer X to A. And then we can transfer Y to X. We can then transfer A to Y. I think that's it. X goes to A. That's A is our temporary variable. Y goes to X. And then A goes to Y. That should swap the 2 values. But we used these 3 registers. So I think that if we call a function and we're trying to store information in the registers before we call the function, it might be bad. But we could always, before calling the function, just take whatever, if we want to keep whatever's in the registers, write it somewhere in memory, call the function, then take the memory back. So I think this is good enough. So let's try swapping. So the output right now is 1, 2, 3, 4 here, according to the notes. According to these colors. 1, 2, 3, 4. So let's try swapping some of these values. But I just realized it's a little more complicated because we kind of need pointers as arguments, right? Because we need pointers as arguments. We want to be able to point to any arbitrary place in memory and then swap them. Let me use the restroom. I'll be right back. Okay, so what I need to do is change this so that it takes pointers as arguments, essentially. Okay, that's going to be quite interesting. So can I do something like this? Now, whatever's here... Does this work? Maybe? Treat it like an address, basically. And then... So what I'm going to do is this transferring data to a temp variable. I'm going to do first. So basically, we need something like load into A. So I'm not sure that this is going to work. Load into A. Whatever arg1 points to. Okay. Now what I need to do is store... Oh, you know what? Let's load into A... Yeah. Alright. Now let's load into X whatever this points into. Now we need to store X at swap arg1, I think. Then store A at swap arg2. This might work. Not too sure about all this, to be honest. Really not too sure about this. So before we write out, let's try to... GSR swap work. This is sort of well, stuff we need to do before we call this function, I think. So swap work. Let's try to swap 3 and 4. It doesn't matter. 1 and 2, 3 and 4. So we need to set these. So I need to... Let's load into X a memory location, which is going to be memory... I wonder if I can just do like this or something. I want it with the offset, but for now, let's just hard code it. So that's the first value. Let's just work with that. So let's load into X that. We don't need to do this stuff. Let me think. What we want is we want swap. We want. Okay, I'm gonna comment some stuff. So we want this to contain something. And we want the other one to contain something. What do we want them to contain? We're treating them like pointers. So we want this to contain, let's say this, and then this as an example. These are spaces in memory, locations in memory. So can I simply load the number 2 into X and then store X to this? Is this good enough? I'm not sure. I'm not sure if this is good enough. And then we swap. Also, I need the RTS here. And swap, I should say jump, I guess. No, JSR, rather. Jump to subroutine, swap, RTS. I don't think this is gonna work. Something's gotta be wrong. Doesn't like that stuff. So there's more information somewhere. So we have these LDA, LDX, LDY. And it talks about these addressing modes. So I don't see anything, for example, here I don't see anything that says indirect addressing, which here we're trying to use LDA with indirect addressing. And so if we go up here, there's indirect, but the syntax is a bit different. Okay. And we'll notice that LDY also has no indirect addressing. So I guess there's a difference between parentheses on the outside and parentheses and then like this. So somebody was talking about this 6502 tutorial. There's kind of an old school one out there. I don't recommend these tutorials here. But if you're learning this stuff, I think it makes sense to use multiple tutorials. They have one where they go into the assembly stuff here. It's for the Atari. They talk about this, and admittedly, I didn't understand what the heck they were saying. I think it's this kind of stuff. Similar to this kind of stuff. Yeah. Okay, so this code will plot a pixel at 0500. So we put 0 into the accumulator. We store that at location 0. And so we're going to have 0 at location 0 and 5 at location 1. Now we set y to 0. And we set a to 1, which is the color white. So it's going to store a, which is the number 1, which is the color white, at this address. And as the y offset, the y offset here is 0, right? I don't at all get this. Is this person making a typo too? That would be horrible. Or am I just not? Probably I'm not understanding. So I think the difference is if you use X or Y. If you use X, you wrap the whole thing. If you use Y, it's separated like this. That's what they do here. I see there's something about time, so I think maybe one is slightly faster than the other. Okay. I don't understand. It's painful. Do not understand. So what I need to do is play around with this and try to make sense of it. Let's change this to 200. This is the first location. So since it's working the way it's supposed to, I'm pretty sure there's no typo. I'm just not understanding things. So I just want this to not have the overlap. Okay. Okay. So this is not... I made the same mistake. It's not putting the number 0 into y. It's because there's no... No, it should be doing that, actually, yeah. So this is 0. How is this not 0, though? This is what is baffling to me. I really don't understand. I'm so confused. What the frick? Let's say we put 4 there. So number 4 goes here. So it's least significant bit, or least, is it bit or byte? Yeah, byte. Least significant byte, most significant. So what I changed here is changing least significant byte. But this makes sense to me actually now. So for the number 4 is here. This is the number 4. Now it's the number 3. It's going to move over. And then number 2. One. This is pixel number 1. Pixel number 0. Zero. I think I was looking at this and thinking that it's loading 0 into A. 2 into A. This is not about bytes of significant and least significant. This is just an offset. So when it has 0, it's... But why somewhere in here above line is same as STA this? So where does it get the 2 from? That's going to be the least significant byte. So I'm still not getting it. Let's change this to, say, number 4. So the number 4, so we've stored the number 2 in memory location 04. Now we're just totally lost. Let's go back. Let's monitor memory, although this part definitely has 0. Why is this part not 0? I don't know why I'm so confused. I think I get it. Okay. think I get it. I think it just automatically does these 2 bytes. So it just looks at the first byte and then looks at the second byte. I think I get it. That was freaking exhausting, though. So unfortunately, I need a break. This was definitely the hardest thing I've had to understand so far. At least for me, it was very confusing. I was misunderstanding things. I think I got it. Thanks, everybody, and hope you have a good rest of the day.